I'm going to talk about basic processes, that the basic time series that we have, and as I introduce the models, I'm going to also talk about the functions that run along these models. Okay, so the very first two models, the very basic ones, is the AR process and MA process, and what I'm going to be doing throughout the talk probably will be changing process and time series using the both names all the time. So AR stands for autoregressive, meaning we have the current value depending on some linear combination of the previous values and some noise, which is current in time, which is the ET. And a moving average process, that would be the situation when our current value depends on the linear combination of the previous values of the noise and the current value of the noise. And so P for the autoregressive process is the order of the process. It means how far back in time we're going. So P is the order, and for the AR and Q in our situation here, it's the order for the MA process. So these are defined as objects in Mathematica. So here I have AR is of order 1, and so my phi1 coefficient is 0.6. Moving average process also of order 1. This 1 here, okay, it refers to the variance of the noise. We assume that the noise is it's a Gaussian noise, and we have independent random variables of mean 0 and variance given by this parameter here. So what we can do, we can generate random function. So I want to simulate the object that the random function returns as a temporal data, and the small 1 in the brackets there tells me how many paths we have in this object. If I apply property path to this, we can list exactly what it's generated. So that's a list of pairs. The first number is the timestamp, and the second number is just the value of the process. So I'm going to create some longer samples, and then I can plot them and compare. And what happens is, often when we look at them, we cannot really tell which one is which. I mean, if you just simulate some AR time series, MA time series, we don't know which one is which. So what we need is some kind of a descriptive functions, and we have correlation function on the process here with the h being the argument, which is the time difference. So I'm going to look at the time difference on the going back in time in that situation. So for the AR process, we see that support is infinite, and for the moving average process, the support is finite. And then there is another function which is also used to distinguish between the two. It's the partial correlation function, and now the support is kind of switched. So we can run these functions for samples, and I'll also see how much they reflect the property of each process to help us identify which is which. Okay, now if we put these two processes together, then we have ARMA, so autoregressive moving average time series. So the current value depends both on the linear combination of the past values, the linear combination of the past noise values, and the current noise. So that's the ARMA process. And here I generate 3 paths. So this is where this 3 is coming from. Path is from 0 to 100, and I generate 3. And this is this 3 that happens to be in the brackets of the temporal data. And we can just plot the paths. So this is how it looks like. What we want to do, of course, is to, if I have a sample, I would like to recover my parameters, maybe of the model, so to find a model. So there are 2 functions which are twins in a way. Estimated process, just as we had estimated distribution in version 8. So I can write find estimated process, it returns the ARMA process. So what I'm giving here is exactly the shape of the model. So I want the ARMA model, or the 1 for the autoregressive part, or the 1 for the moving average part. And this can also be achieved providing ARMA 1,1, which means just give me the model ARMA with such orders on autoregressive part and the moving average part. So some properties. So I have to define my process and object, and those who went to Roger's talk earlier today know that this is a distribution. So the value of the process at given time, it's a slice distribution. In this situation for ARMA, it's a normal distribution. When I have 2 times and I slice this at 2 times, I need to have a binomial distribution. And what you observe here, that there is a dependence, so we don't have just a bunch of independent random variables running around. So the things work from statistics, mean, variance, and interestingly, what's the probability that at time 2 I'm gonna have the value of the process being larger than 3, and we used to be able to do this x distributed as a distribution in version 8, and now we're gonna have x distributed as a process, so running all these properties on the process. Correlation function. So when you look at the structure here of the correlation function, you see that it depends only on the difference of the times. So only the absolute value of s and t comes into play. So this is another property for the processes in general. So if we have mean which is constant, and we saw before that mean was 0 for this process, and the correlation function depending only on the time difference, such processes are called weakly stationary. And this is our small utility function here. Tell me if my process is weakly stationary. It's called weak stationarity. And there is no Q there because besides returning true or false, it can return conditions if you give it a symbolic parameters. Okay? And also you can observe here that the conditions here depend only on the autoregressive part. Moving average processes are always weakly stationary. That's a correlation function and partial correlation function for the process and for the sample. So you can see that both correlation function and partial correlation function basically has infinite support in this situation. Okay, ARIMA, that's going to be now another model which is integrated ARMA, which basically means that I have an ARMA process and then I accumulate the values in the ARMA. And this is the equation with the operators. At some point writing the equations only on observations, it's not handy. And D here, this is the new parameter comparing. So we have the ARMA process and we now having integrated ARMA, so we added new parameter in between the lists. So the integration order must be an integer. So I can define a few ARIMAs and then create samples for D being 0, 1, 2, and 3. I should plot to see what happens. So for D equals 0, we should be back to ARMA, so it's a stationary. And for D equals 1, we have a linear trend. For D equals 2 and 3, we are getting into the situation when we have polynomial trends of order D. So I would like to estimate, so I can estimate ARIMA, and this is another new function which is time series forecast. So I would like now to know if I have my samples, I have my model estimated from the sample. I would like to forecast future values based on this model and on this data. So that's not purely a simulation when I have no information of what happened in the past, but this is a forecasting based on my past values. So I create a forecast and then I can see that the forecasting follows the general trend on the time series here. Okay, so let me show the plot first. So what I have here are two samples. One sample is generated from the pure ARMA. So I have here ARIMA with integrating order 0, and the second sample is generated from ARIMA with order 1 of integration. When you plot this, they kind of look alike. I mean, this is my choice of example, but many times when you plot many of them, you just don't know from the plot whether there is a linear trend or not. And that's an important question to identify in the sample, whether you actually have a linear trend, and if you want to analyze your sample, whether you need to, detrend it or not. And the tool for this is the unit root test, which is a hypothesis test to find out whether our sample comes from a model with which is integrated or comes from pure ARMA model. So if I run it on the first sample, I mean, luckily, I need to reject the presence of the what we call unit root, but that means that the model is integrated model. It's an integrated ARMA, and if we run it on sample 1, we see that we cannot reject this possibility. So this works as our usual hypothesis tests, and we have few tests available here. So we have the Dickey-Fuller F and T, and then Phillips-Perron F and T tests. And you can see the p-values being either very small or being above the significance level here. Okay, adding S to ARMA will give us a seasonal autoregressive moving average, so SARMA process, and that means that I now have orders of here. That's actually maybe look at the polynomials. So I have my polynomials here with also with a seasonality component. This is governed by parameter S. So now we're getting somehow the double amount of autoregressive orders and moving average orders. That means that I can have the standard autoregressive dependence, so it's the linear combination of the previous values plus the seasonal autoregressive dependence, meaning I'm only depending on the linear combinations of the past values, but that happened every season going back in time. So we have a SARMA process here. The first two lists are empty, so that means that my standard ARMA coefficients are 0, and I set the period to be 12, and this is the seasonal autoregressive list of coefficients and the seasonal moving average list of coefficients. And let's see how this looks like. It oscillates around 0 in somewhere. Is it stationary? So in our example, yes, that's a possibility here. And when we look at the general SARMA process with symbolic parameters, we see that this weak stationarity depends on the AR coefficients, both the standard ones and the seasonal ones. So what we can do, we can represent SARMA as an ARMA process. Okay, but you can see that suddenly the orders for ARMA are becoming really, really large, and so this is the reason why the SARMA model was introduced to actually deal with short orders on the process, on the model. And when we plot the correlation function, you see that it has spikes that happen at the multiplicities of the season here. Okay. So I would like to show an example, which is a temperature prediction, and I evaluated this data. It's a weather data from Mathematica. It's from Champagne. What I'm looking at is hourly readings of the temperature, and I'm gonna package it into temporal data, and I'm taking the first 300 hours of the observations, and this is more or less how it looks like. So that's June, and it's in Celsius. So just to make the right reference, what I would like to find out is, can I model it with a SARMA model? So I assume here that my season is 24 hours, right? It's a daily change in the temperature, and I find my model here. What I would like to do next was to find forecast. Okay, so my process is the estimation temperature, and this is how far I would like to go. It's 3 days ahead, and see what to expect. Okay. So we kind of see that it goes down. I mean, the last day in our observation was not very hot, so we see the temperature. What would happen if we know more? So I'm adding a new day to my observation. So I'm taking from the weather data, I'm taking 24 hours worth of new observations. Okay, so this is the yellow part here. So we see that actually the temperature during the day that we are forecasting here was warmer than what we forecasted. So we were off in that sense. What I would like to do now is to adjust this forecast for the remaining 2 days using this information that we know, that we have. So we know that we overshoot the temperature. We forecasted that it's going to be colder than actually it was. So just using one function, I would like to improve this forecast. So what I give here, it's the same model that we were using. It's the forecast that we already did, and I'm adding the new information, which is the new day data. And so our new forecast, it's all in yellow. Okay, and you can see that the first day, the first bump in the new forecast, it's exactly our data that we inputted as a new data here. Okay, so a few words about the forecasting functions. So here I have SARIMA process, that's another one. So SARIMA will be standing for the seasonally integrated ARMA, to make it shorter. And what we have here is the structure coming from ARIMA. This is exactly what we have in ARIMA part. So the autoregressive part, integrating order, and then moving average part. This is the season, and then we have all the same parts for the seasonality components. So what we have here is the sample. So I can sample this and see that as we proceed with the season, our process is varying more and more because of this integrating order that happens here in the seasonal part of the coefficients. So running forecast for the 30 more days or more time steps observations. This is the path, and we can plot it all together. What we can do also is to access mean squared errors from the forecast. So these exist already in the forecast variable. When I ran the time series forecast on that, they were calculated then there, and I can just access them via the property. And what happens is that we are getting a temporal data again, and basically for each timestamp I have assigned the error of the prediction. We can create error bands, and we can then transform them into some confidence bands on the forecast. So this is how it looks like. The blue is the forecast, and then our errors keep going. So then the adjust time series forecast. So assuming I have new data, and you see I'm kind of manipulating with the timestamps. So our data here was going up to the 100, right? I have a forecast that goes up to 130. I create now new data that goes from 111 to 112. And so create the adjusted forecast on this. Okay, that's the path. Whoa. Okay, so that's our adjusted forecast. And I look at the new data. Okay, it starts with a timestamp 111, and when you look at this part, which is in between, so for the stamps 111 and 120, then the adjusted forecast is exactly the same as the new data. And so I can plot this, and we see that we have the old forecast at the beginning, then there is a new data, and then there is an adjusted forecast. And I can the same way, because the adjusted forecast is again a temporal data, so I can create the error bands on this. And then you can see that this is the part of the old forecast. Then there is a new data coming in, so there is no errors because that's exactly what happened. And then we have the adjusted forecast for this. So that's the that's the two plots, and so, and I think I'm at the end. So. Okay.